All right, guys, we have arrived at our last video for the semester. And in this video, we're going to continue talking about U substitution and integrating using U substitution. We've got a few more examples I want to show you, including what to do when we have a definite integral and when we have to use U substitution to find the integral. So let's take a look. So we've got the integral of x times the square root of 2x minus 1. So it's still an indefinite integral. And take a look at it and see what you think a good choice of U would be. There's a function here that's inside of another function, and hopefully you see that that would be 2x minus 1. Here's kind of the issue or the twist in this problem, is that when we take the derivative of this, we're going to have 2, right? 2 is a constant, so that's not a problem. But when we make our substitution, we've got to have something to replace this x that's sitting out front. And we're not going to get there by taking the derivative. We're not going to get an x out of this derivative because the function is 2x minus 1. So the derivative would just be a constant. We need to have something, though, that we can replace this x with. So when that happens, and let me just finish what I was saying here. So the derivative du dx, of course, is 2. We can replace dx at the end with du over 2. Again, not a problem because the 1/2, the over 2 part, is a constant. But we still need something for this x in the front. So what we can do is we can go back to this expression we had for u, and we can solve for x in that expression. So if I add 1 to the other side and divide by 2, I get x is equal to u plus 1 all over 2. So that can go back into my integrand and replace the x that's in the front. So what I have is u plus 1 all over 2 times the square root of u, which is now u to the 1/2, times the dx, which gets replaced with du over 2. Now, I realize at first glance this looks more complicated, right? It doesn't look like we've made this any simpler to work with. But here's the thing that we've done. When you have a radical and you have multiple terms under a radical, it's always more difficult to integrate that than if you can make it so that you just have a single term under the radical. And that's what I've effectively done, is I've made that 2x minus 1 into a single u under the radical. I'm writing it as u to the 1/2, but that's the square root of u. I realize there's more terms in front, but that's not a problem because we can do some algebra here and simplify this. I couldn't do that with the multiple terms that were under the radical, but now I can take that u to the 1/2 and I can distribute that. So when I distribute that, that gives me u to the 3/2. Make sure you see that. U to the 1/2 times u to the first is u to the 3/2, and then u to the 1/2 times 1, of course, is u to the 1/2. And then this 2 that was in the denominator, I moved it to the front with the 1/2 that was already there and got 1/4 in the front. Now I can use power rule. So kind of the moral of the story here is if you've got multiple terms under the radical, you need to figure out a way to get that to be a single term when you do your U substitution. Now we can use power rules. And so I'm going to write this as u to the 5/2 over 5/2, right? U to the 3/2 plus 1, which simplifies to 2/5 u to the 5/2. Plus u to the 3/2 over 3/2, which is 2/3 u to the 3/2, times the 1/4 in the front. And then just go back and make sure you make your replacement for the u's, which was 2x minus 1. And then I also distributed the 1/4, although you don't have to. You could have left the 1/4 in the front, and that would have been just fine. Okay, when we're working with a definite integral, so the integral from a to b, the technique is similar, but there's one thing we have to take care of. And actually, there's a couple options we have here. Let me show you what the options are. So let's look at an example. We've got the integral from 0 to 1 of x times x squared plus 1 quantity cubed. So hopefully you see that if I let u equal x squared plus 1, that's a good choice because the derivative will contain an x, which is what I have in the front. So that's going to be an easy substitution. Du dx equals 2x, so du equals 2x dx. Solve for the x in the front and the dx at the end. That gives me du over 2, replaces the x dx. Now, here's the thing you have to watch out for when you have a definite integral. This 0 and 1 were the limits of integration when I'm integrating in terms of x. If I'm integrating in terms of u, which is what's going to happen in a second, these limits need to change. They need to shift to match whatever your choice of u is. So when you have a definite integral, what you're going to do is you're going to take the lower limit, in this case 0, substitute it in for x into your expression for u. And that's going to give me my new value in terms of u. So when x was 0, the value that corresponds to that in terms of u is now 1, because 0 squared plus 1, of course, is just 1. When I replace x with a 1, or I substitute 1 in for x, I get a u value of 2. So now my new integrand looks like this. We've got u to the third times 1/2 du, but the 1/2 moved to the front, and I've got 1 to 2 as my limits of integration. Okay. What I don't want to see is that you've written it in terms of u and you've left the 0 and the 1 in here. That is not okay. The 0 and the 1 applied to the limits in terms of x. But if you're writing it in terms of u, you need to have new limits going from 1 to 2. Now we're going to integrate this. So we've got u to the fourth over 4. Now leave everything in terms of u. So when you integrate and it's a definite integral and you've changed those limits of integration, everything's in terms of u now. So leave the limits in terms of u, leave the expression in terms of u, and apply the fundamental theorem of calculus. So we've got u to the fourth over 4, replace that with a 2, and then u to the fourth over 4, replace that with a 1, and take the difference and simplify it, and you'll get 15 over 8. Let's try another one. We've got the integral of tangent x secant squared x from 0 to pi over 4. So hopefully you see that if we let u equal tangent x, that's a good choice because the derivative will contain secant squared x, which is exactly what I have in my integrand. So let's get the new limits of integration. So if u is tangent x, then u of 0 will be tangent of 0, which means 0 is still the lower limit. U of pi over 4 will be tangent of pi over 4, which is 1. So my new integrand becomes the integral of u du from 0 to 1. So we're going to find the antiderivative in terms of u, so u squared over 2. Leave it in terms of u because you changed the limits to go with u. So apply your fundamental theorem of calculus. And so we've got u to the second, so 1 squared minus 0 squared leaves you with 1 times the 1/2, leaves us with 1/2 for our final answer. We could leave the limits alone. This is an alternative. You can leave the limits alone and go back and replace everything in terms of x at the end. That is another option. Let me just show you if we had done that. And actually, do you see that's not right? Because what's the problem here? I've got u du, but what's the issue with the limits? These limits are the original limits, okay? So if you're going to do it, leave the limits out until the very end. So I've got the integral of u du, which is u squared over 2, and then go back and change that to tangent x, and then you can work with the original limits. So we've got tangent of pi over 4 squared times the 1/2 minus tangent of 0 squared times the 1/2. Notice that we get the same answer. It's really up to you which way you do it. But what I don't want to see is that you've done something like this, where you write the integral in terms of u and you leave the original limits. That is not okay. If you write it in terms of u and you want to leave the original limits, leave out the limits till the very end and you go back and substitute in terms of x. Or go ahead and change the limits to be in terms of u and work with u the entire time. Either way you do it is fine. Usually it's more work to do it this way, where you go back to x, because the more complicated your expression for x is, the more complicated this is going to be. And we'll go over it in class and we can do it both ways. Let's try one more here. We've got the integral of 3x squared times the square root of x cubed plus 1. We're going to go from -1 to 1. So think about what you're going to use for u. U should be x cubed plus 1. The derivative will contain an x squared. Actually, the derivative contains 3x squared, which is perfect because I have a 3x squared in the front, times dx. Let's change the limits here. So u of -1, the lower limit, will be 0. Make sure you see where this is coming from. Plug -1 into x cubed plus 1, and you get 0. The upper limit of 1, if you plug in 1, you get 2. So now we're going to go from 0 to 2 of u to the 1/2, that's the square root of u, du. Antiderivative is u to the 3/2 times 2/3. Fundamental theorem of calculus. Evaluate that expression at 2 minus the value at 0. So I didn't write out all the steps here, but the lower limit, if you plug it in, is 0, so I'm not worrying about it. So we have 2/3 times 2 to the 3/2. And You can leave it as 2 to the 3 halves. They wrote this kind of a weird way in the PowerPoint. But this would just be, this 2 radical 2 is because you've got the square root of 2 cubed. 2 cubed is 8, and they simplified that. That isn't necessary. You could actually leave your answer just like this.